Hello everyone and welcome to 3.5, which deals with tree and Venn diagrams. So let's get into what they are. A tree diagram is a type of graph that's used to talk about the outcomes of an experiment. Okay, so basically here are the different things that can happen. It's just a nice graphical way of talking about it. So these are called branches. This one actually like it when you have here, this is usually the branch here, this is a branch, here's another branch, here's another branch, okay, here's a branch, and here's a branch. So let's say, for example, here, let's say there are two balls in one container, okay, an urn. Let's say you have a red ball in the container or a blue ball, okay, so let's say if you draw two balls one at a time with replacement, meaning that you put it back in, right? So these are the possible outcomes. So if you draw once, you can either get a blue ball or a red ball. Okay, that's the first draw. On the second draw, since you're replacing it, you can get a blue ball again, or you can get a red one this time. And then if you had drawn a red ball, then you would either get the same result. Like you could either get a blue ball or a red ball on your second try. So here are all the possible situations, and you can kind of, as like here are the paths. So the first path would be here, I did blue, blue. So here's blue, blue, right? This is one outcome. The other outcome could be blue, red. And that's, you could see it here where it's blue and then red. Here's the third outcome, red or blue. And then the other one, red, red. So you have blue, 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 red, red, blue, and red, red. Okay, so those are four outcomes. And so now you can see how the tree describes the different outcomes. Okay, if there were more balls, we would have so many branches. So sometimes we can we can simplify this by having one branch represent multiple branches. Okay, so let's suppose you had 8 balls. 3 of them were red, so 3 are red and 8 are blue. So we could depict that as 8 blue and 3 red on the first draw. You could either get 8, you could get one of 8 or one of 3. So these are all the different, this 8B represents 8 possible branches for all the blue ones. And this 3R represents the 1, 2, 3 red balls. Okay, out of those 8B, if you replace it again, it's the same thing. You're going to have the same choice again and the same choice again. Okay, so instead of drawing all these different possibilities, what you would do is you would say, okay, well, you would multiply the branches so that you could get the total number here. So you would get 8 times 8 is 64. 8 blue, and there's 3 red possible, so the total would be 24. Blue-red options. If you drew one of the red balls and then a blue ball as the second draw, you would get 24 possibilities of red and blue. And then finally, if you drew a red and then a red, there's 9 possibilities of getting that. So those are all the frequencies. So 3R represents R1, R2, R3, 3 different branches. 8B represents the 8 possible blues. And then when you see this 9RR, it could be red 1 with red 1, red 1 with red 2, red 1 with red 3, red 2. So all the combinations, okay? So it's just easier to multiply. And that's what I just said right here. And that's the same thing that I just said. Okay, so then here, there's 2 positions to fill with replacement. Okay, so going back to this. So how many possible outcomes do I have? Okay, so I have 11 possible choices for the first draw, and then I have 11 total possible for the second draw, so that gives me a total of 121 outcomes. Another way to think of it is that you could add these numbers at the end, and that will give you all the possible outcomes. So if I add 64 plus 24 plus 24 plus 9, I get a total of 121 possibilities or outcomes. Okay, so let's continue. So if you were to list the 24 blue-red outcomes, right? So let's say we had blue ball 1, ball 2, ball 3, ball all the way to ball 8, and then 3 possibilities for R. Could you list them? And if you could, it would look something like this, right? It would actually be this. So it's a lot. So I mean, you can even count them. There are 24. Now, if we could say, what's the probability of getting two reds? Okay, so let's think about this. Okay, what would this be? How do we calculate probability? We calculate, okay, the number of events occurring that we're interested in over total possible outcomes. So do you think we have it? So number of possible events over total outcomes. So if you guessed 9 over 121, you are correct. Okay, so another way to think of it is to get a one red ball first, it would be 3 out of 11, and the second one would be 3 out of 11. And this is, yeah, so that's another way. So what if we wanted to do an OR? So if we wanted to do an OR, remember that's addition. This is also multiplication, right? Probability of getting a red ball is 3 out of the 11, and similarly, so, you know, when you multiply them, you get 9 out of 121. So remember, this would be P of, you would get P of RB plus P of BR, and then if there's an intersection, you would do that, but there isn't, so you would do P of RB, okay, that's 24 out of 121, right, RB, and then BR is also 24, so the total would be 48 out of 121, so there's two ways to do this. You could do, you can multiply the branches, right? Or I mean, multiply the probability of red times the probability of B plus the probability of blue times the probability of red. Okay, cool. And then let's continue. How about if we wanted to do calculate probability that we got a red on the first draw and a B on the second draw? Okay, so it has to be red and a blue, right? So it's the same thing here. It's 24 out of 121. So let's say, what if you wanted to do, let's do the probability of getting a red on the second draw given that you had a blue on the first draw. So given, remember that that's it shortens your sample space, your sample size, I mean. So this is a conditional, right? So one way to think of it is, okay, let's look at how does the sample space get reduced? The condition is this: you have to draw blue on the first draw. So these are all the possibilities here that have blue on the first draw. Okay, so now your sample space has been reduced to 88, right? 88. Okay, now if you want to know that you draw red on the second, that's this, right? That's 8 first and then a red. Okay, so there's 24 total out of 88. Okay, so there's 24 possible outcomes out of 88, which is 3 over 11. Okay, so now let's talk a little bit about Venn diagrams. What is a Venn diagram? So we talked about that earlier, right? This is just us, we're just reintroducing it again. So we have a box that represents everybody, the sample space, and then you have here, or a rectangle, you have two circles or ovals, and these circles or ovals represent events. So let's suppose you have an experiment with the outcomes being the numbers 1 through 12, which each outcome has an equal chance of occurring. So let's A be the numbers 1 through 6, and let B be the numbers 6 through 9. So the intersection of A and B is the number 6, and A or B would be everybody, 1 through 9. Okay, so this is what the Venn diagram would look like. Okay, so let's say here, suppose an experiment has outcomes black, white, red, yellow, orange, green, blue, purple, okay, where each outcome has an equal chance. So let's suppose that C consists of green, blue, purple, and event P consists of red, yellow, and blue. So then the intersection of them is blue, and C or P, the union, would be all of these: green, blue, purple, red, and yellow. So this would be the Venn diagram representing that situation. Okay, finally, let's talk about Bayes' theorem a little bit. So Bayes' theorem, we've already talked about this. Remember that the intersection, the probability of an and or an intersection, the way you can think of it is, you can say this as an and, or you can say this the intersection of A and B. It's equal to the product of the probability of A times the conditional probability of B given A. Now, if you solve for the conditional probability, you get the probability of A and B over probability of just A. So, and you can also think of this in terms of, like, you can represent A and B as P of B, P of A given B. So notice that you can also flip this, because sometimes you're going to have these two, sometimes you'll have these two. It just depends on the context of the problem. Okay, so let's look at an example and see if we can use this Venn diagram, this tree diagram to help us solve it. Okay, so let's say the probability to have type of cancer in a population is 3%. A test for the disease is 99% accurate if the person has the disease, and it's 98% accurate if the person does not have the disease. What's the probability of a person having the disease if the test result is positive, meaning that the person the test indicates the person has the disease? So let's look at this tree diagram is kind of sideways, but it's fine. So here, look, it's 3% of getting a cancer diagnosis. So that means that 97% of the time it's going to be no, they don't have it. And then out of them having cancer, if they take the test, 99% will say yes, it'll be correct 99% of the time. So that means that 1% of the time it's going to give you a false negative. It'll say that it'll say not you, but it'll say that the person doesn't have it when they actually do. So this is the event of they have cancer or don't. And if they don't have cancer and they take the test, 98% of the time it'll be accurate, where the test says no and the person actually doesn't have it. But 2% of the time it'll give what we call a false positive. All right, so let's see. So, okay, so here we go. So putting this into, mathematical symbols here, we would write probability of cancer P of C being 0.03, P of NC is 0.97. Probability of getting a yes given that you have cancer, or that the person has cancer, would be 99%. And the probability of getting a no given that the person has cancer would be 0.01. Then the probability of having getting a yes considering that they don't have cancer is 0.02%. The probability of having no if the test saying no, or being, saying no, you don't have cancer, if they don't have cancer, meaning that it's accurate, is 98%. So here's all the tree diagram in symbols here. So, in mathematical notation. All right, so let's continue. So if I wanted to say, what is the probability of, what was the initial, I don't even remember. What's the probability of a person having the disease if the result is positive? So meaning they want to know what's the probability of somebody having cancer if they get a yes. So it's kind of backwards, right? So we're going to use this variation of Bayes' theorem. So, so probability of B given A, and then it's, instead of the and, we've written this in terms of conditionals. So this is what we're doing here. So this would P of C times P of yes given C all over P of yes. Okay, so we're just applying this theorem to this situation. And we have P of C, we have yes given C, we have P of yes, right? But how did we get P of yes? What's the probability of yes? So it's the probability of yes is the probability of getting a yes when you have cancer, and the probability of having saying yes when you don't have cancer. So these are all these are the two paths. You have this path and you have this path, right? So so this one is considered the conditional, but remember the product of these two, right, is going to be the and. So yes given C times P of C plus probability of yes given no cancer times the probability of no cancer. Because we have to multiply these two, so that's 99 times 0.03 plus 0.02 times 0.97. So this represents here the entire probability of getting a yes, okay? So then when you plug this in, you get 0.6049, and that is how you use this. So that's it for 3.5. Here's your homework. Remember to study for your exam. I posted up the review so you can go ahead and do sample problems, but the quiz will be released tomorrow and the exam will be released on Thursday. All right, see you guys on chapter 4.